if industrial machinery breaks, all of you might be affected. Think about an energy plant. If the energy plant needs to shut down because some critical equipment fails, then all of you might sit in the dark. More generally, critical equipment failure can lead to safety critical situations and higher costs. That's why companies with critical equipment employ maintenance strategies. Have a look at this PF curve. It illustrates how over time potential failures develop to functional failures. The functional failure is the point in time when the asset can no longer perform as expected. However, we know that in around 20% of the cases, the asset shows early signs of failure, so-called potential failures. Let's take the example of pumps, for instance. In pumps, unexpected changes in vibrations may indicate potential failures. Predicting those changes can help you for predictive maintenance. So this brings me to my research. In my research, the goal is to enhance domain experts' ability to comprehend the performance of industrial assets. More specifically, I want to first alarm operators about potential faults, and second, to help with the diagnostics of these potential faults by making the methodology interpretable. So I told you before that the changes in vibrations can indicate in some industrial assets like pumps upcoming faults, potential failures. However, it's not that easy. Because industrial assets operate in highly dynamic environments, it can be that also other operational contexts can influence these vibrations. For instance, in the example of feedwater pumps, it could be the rotational speed, or for instance, the water flow that impacts the vibrations. However, that's not a sign for potential failure. By the way, this also holds for other industrial assets like gearboxes, which I also looked at in my research. So the key question is now how to deal with the operating context obfuscating the performance readouts. In our methodology, we deal with the operating context by explicitly modeling the context and the performance in two separate views. In the process view, which you can see on the left, the operating context is characterized. It includes parameters such as, for instance, the rotational speed or the flow, but also other parameters that have something to do with the operational behavior of the industrial asset. On the other hand, we have the performance view. The performance view characterizes the asset's performance. So changes in the vibrations should indicate potential faults. Now, in the methodology that I'm going to show to you, we have two phases. The offline phase on the top, where we model the asset's healthy behavior, and the online phase on the bottom, where we detect the actual anomalies online. But let's start with the offline phase. The goal of the offline phase is to model the asset's vibration fingerprints in a contextual manner. So how do we do this? We actually do it by splitting the operating context in a set of operating modes, which you can see here on the left. And then for each of these operating modes, we associate the expected vibrations, so-called vibration fingerprints. With these operating modes and context-sensitive fingerprints, we are able to model a healthy asset. Now, in the online phase, it comes to the anomaly detection. But first, we need to make sure that we predict the operating context correctly. And more importantly, it could be that new operating context emerges on the line. For instance, a different combination of rotational speeds and flow, and we should make sure that we detect that. This is done by comparing the operating mode representatives that you can see on the right with the actual operating point of the asset at the moment. If they are very different, then we will just an unknown operating mode. Once the operating mode is detected, we can turn to the actual contextual anomaly detection. This is done now by looking at the fingerprint, at the vibration fingerprint, and comparing the observed vibrations of the given context to the contextual fingerprint. If it's approximately the same, then there shouldn't be any problem. But if there's a bigger difference between the two, then this is a sign for potential fault, and the equipment should be checked up. Thanks to our industrial partners, we were able to show that in a real-world industrial use case of industrial field water pumps, that we can detect anomalies in that use case and changing operating context. In the given example, we have detected a prolonged period of anomalies over multiple weeks, and we could link this to increased vibrations at one specific location within the feedwater pump. But we had also many other examples. So, if you want to know more about methods that link studies of failure mechanisms to prognostics and health management, then have a look at this use case, prognostics and health management. Talk to me or to my colleagues. If you want to know more about the specific work that I was involved in, you can have a look at these publications or also talk to me after this talk. We were only able to validate our methodology on a use case of real-world industrial data thanks to the AI Icon project Conscious. Together with our industrial partners and other academic partners, we also developed other contextual anomaly detection methods, and we applied them to real-world industrial use cases. Finally, thanks to the compact enrichment project, we were able to further streamline our methods, and we will make soon a starter kit available for non-AI experts. Thanks to all of these puzzle pieces, we were able to illustrate that we can detect potential faults in a real-world industrial use case as early as possible. And you might not sit in the dark.